today. So again, thank you for inviting me and Mr. Fawad for this workshop. And if you are interested in pursuing your postgraduate studies at FKE or UTHM, please do contact me. And if you have any question regarding the topic presented, we are happy to answer it. Okay, Mr. Fawad will do the presentation. Okay, thank you.
Thank you very much, Doctor.
Yep. Yeah, okay. It's over to you, Mr. Fawad.
Yes. Are you getting my voice?
Yes, yes, I think we can hear.
Okay, so thank you very much, Dr. Noorzali. I'm going to start my topic today, image classification. So as Dr. Noorzali already gave his introduction, I'm just going through this. This is my introduction. Then these are some of the publication in the area of image classification and segmentation. We have recently published multiple papers in high impact journals. Now let's dive into the content of the workshop. Now here I'm going to start with what is image classification, the basic definition there, and then find out the semantic gap between the human and the machine. Then what are the challenges find the computer to just classify any image. Then ask for some basic level of solutions for edges and corners, then nearest neighbors, then how to set up the hyperparameters, then find out the limitations of different algorithms. Then I'll go directly to the deep learning side, how image classification can be performed in deep learning. Then what are the steps in image classification, type of image classification, then convolutional neural network, and the code in Keras. So to start with, I'm just going with the definition here. Image classification is just a computer vision process that can be classified an image based on visual information. For example, when you do image classification, your computer received any input image, which is a cat in this example, and the system is aware of some predetermined set of categories or labels. So some of these might be like dog or cat or truck, and this with some fixed set of category labels. So the job of the computer is to look at the picture and assign it on any of the fixed labels. So this can be an easy problem for a human being to just pursue and just find out and classify. But what for the machine, it will be very difficult to how to classify any object inside any image. So there is a semantic gap. Basically, a computer sees normal numbers of a bunch of, you can say, a grid of numbers between 0 and 255. So for the normal human being, is just an image which can be visualized from your eye and can be identified in your mind, and then it will give the answer that will be a cat or a dog. But for a computer, it's just the set of numbers from 0 to 255, which in our language of image processing, you can say it just a pixel values. So there is a semantic gap between all these things to understand between this. So there can be three channels, R, G, and B, red, green, and blue. So this can be differentiate with different channels. For example, here I consider an 800 into 600 into 3 size of image. So normally the challenges which the computer face during the classification of any image is normally I'm considering here 6 points. Number one is viewpoint variation. I'll discuss later on one by one. Then the elimination, deformation, occlusion, background clutter, and interclass variation. So for the viewpoint variation, this is the major problem which computer can find out. When change the direction of a camera, but the object is still on the same position, all the pixel value is changes. For example, if any live object is sitting around and you take a picture from the left side, and after some time you'll take a picture from the right side and from the front side, the pixel values will be changed. So we need to make any robust algorithms to detect this kind of problem. So for the second, we have elimination problem where we have different lighting conditions. For example, if any object like here in this pictures, you can see there are different cats are sitting with different lighting conditions. So it is very difficult for a machine to identify it. How can we or what are the pixel values of each cat inside this image? So there can be a deformation. For example, an object which is a live object can change its position or poses from different conditions. So it will again a very difficult for a machine for getting every time to find out to classify is it a cat or something else. So another part is the error is the problem is on the occlusion. You can easily sometimes see that there is a part of an object can be available to display in any picture, as you see in the picture 1, picture 2, and picture 3. In picture 3 there is a cat is inside a couch, or in picture 2 a cat is hiding inside some bushes. Then the cat 1 is inside some kind of close upper it. So it's very difficult for a machine to identify exactly what is the object in that particular picture. So these are some major problems which a computer has finding out. And another one is a background clutter. Background clutter seems to be the part of a background and quite similar to a foreground. Sometimes the color of a cat is very similar to the foreground or environment which is available on that. So it's again a very difficult for a machine to detect this kind of problem. So sometimes there is interclass variation where are different visual appearance of the object, like different sizes, shapes, colors, and ages. So normally, again, the features of all these objects can be identified with some kind of matrices or some kind of features which can be calculated. And we have some basic solution out of it. In solution 1, previously we have to find out the edges and corners. But again, it's very brittle and it's not scalable, because, for example, if a cat has ears and eyes, so you need to draw some kind of, or you need to define some kind of policy every time the cat has this kind of ears or this kind of nose. So this can be brittle. That means if there is some kind of noise or distortion inside that image, then it will find out, it will wrongly predict any kind of thing. So this can be one solution to find out the edges and corners, but I think it's not reliable to find the proper image from an image. So there can be another solution for that. Either we can make any algorithm. So for that we may use nearest neighbor can be used. We can just make a small program out of it, in which just memorize all the data and labels and predict the labels of the most similar training images. But what do you think? Is it better than that? Yes, you can see in some cases there can be used as better results, but have some limitations out of it. So for example, I'm taking here a nearest neighbor with Cypher 10 data set, in which you can say there are 10 classes, in which 50,000 training images and 10,000 testing images. You can find out the test images results as you see on the red small boxes there. The prediction is not accurately done. So I can say that the nearest neighbor is also doing not a proper classification method for having this solution. So basically, this nearest neighbor using a Manhattan distance, in which it will compare the testing image pixel value to the training image value. For example, if you check on the left hand side 56, and on the right hand side training is 10, when you just subtract it, it will give a 46, the pixel value on the absolute value difference. So after that, the pixel values is just changes and having this kind of comparison, and after all the values of other remaining pixels has been added to this value. But this is again not a proper approach for getting this. So we have another method of k nearest neighbor, in which we have different values of numeric values of k's. For example, if you see in the diagram, there can be k can be 1, k can be 3, k can be 5. Normally we assume that it can be an odd numbers, because it will just compare the adjacent neighbor's distance. This can be done with using Euclidean distance or Manhattan distance. So as you see in the figure, there are 5 different areas having marking with blues, greens, reds, and yellows. Whenever whenever you change the value of k, the area, or you can say the boundaries, the decision boundaries is changing. So again, it's again, and you can say an hit and trial method that you will find a better solution. Which one is better? For example, in our case, K with the value of K, it will shows a better result other than K3 or K5. So K nearest neighbor normally uses Manhattan distance and Euclidean distance. So in Manhattan distance, normally we will just calculate in the form of triangles. Then in the Euclidean distance, we will just find out the pixel values with x1, y1, x2, y2, and having this formula. So you can see the difference between the two. If you applied Manhattan distance with Euclidean distance, you can find the in figure number 1, you can easily find that the decision boundaries changes. Like for on the green color, you can just imagine the green color here on the upper side and the green color on the upper side. You can say the decision boundary is changing according to the formula. So it means that it will depend upon yourself to finding which method is which formula is better for your classification. Sorry. No. So now we are going to having setting up hyperparameters. So hyperparameters are normally the values which can be adjusted for the training to get the better results. So there can be multiple ideas. In idea 1, you can say you can just take all the data set here. It can be better, works always perfectly on training data. But again, it cannot be a better idea. So we have another idea, just split the data set into train and test. This can be a good idea, but the results can be like every time they split the data into test, train, choose hyperparameter, that will not perform exactly as you like or the requirement. So if you are asking for the third idea, which is a quite better idea, we can just split the data into train, valid, and validation and test sets. So again, normally there is another cross validation method. We can just split into folds. There are different folds. You can say just split the data into different batches and different folds to find the average value and results. And normally it will be applied on the validation side. So the limitations of k-means, k-nearest neighbors have a dimensionality issue. For example, if you have a single dimensions or a 2 dimension, that it will be easy to understand and easy to just get the values. But whenever the dimensions will be increased, then it will be very difficult to get the better results from the adjacent neighbors and to design a decision boundary. So now moving forward to the image classification on deep learning. So deep learning, in deep learning, we achieve image classification by extracting features. So features are just the values and the numeric pixel values from different images and classifying them based on their features and neural networks. So these are the steps in image classification. We have number 1, the most important part is the data. So we need to have find out the data and the quality of the data. Then we have to pre-process it, then have a feature extraction. Then selection of training data means which algorithms or which method and which procedure will be adopted to train the data. Then have decisions and classification output, and then after all accuracy assessment. So there are 2 types of classification. One is supervised learning and other is unsupervised learning. So in supervised learning, we have 4 steps in which user collects the training data first. Then the user specify the training sites to be used for the classification. Means a user can select a sample pixels in an input that are representative of a specific class. So a supervised classification algorithm is required a training sample of each class. This is very important. So computer assigns a pixel to the closest class based on the training data. Then after the last step, they will just evaluate the results. So in the supervised unsupervised classification, user just selects the number of classes, then computer cluster it means that it will make some cluster out of our group of these pixels into special classes, then label the cluster corresponding to the informational class, and then evaluate the results. So in deep learning, just the basic formation, we are going with start with the linear classification. The linear classification is just the mathematical formation or mathematical function of image X and its parameters or weight W. As you see, X is the image, the blue value is image, and the W is the parameters or the weight. Here I take 32 into 32 into 3 channel image, means that the image size is 32 into 32, and 3 is the number of channels RGB which is used in this. So the 10 numbers of giving classes, I have just already told you that I'm using here a Cypher 10 dataset in which 10 classes are there. So the prediction can be made after this linear formation, linear classification inside this 10 classes. So in linear classification, we just multiply the values of X and W. That means the value of the images, the value from the image, I mean the pixel value of the image, is multiplied with its parameter or weight. For example, here, there is 10 classes and have one multiplication, then X is 3072, which will be get after having 32 multiplied by 32 into 3, you will get 3072, and X is 1. Here I'll take only one image, that is X is 1, then the value is 10 into 3072. So you can easily get that there can be 10 into 3072 values of from this giving number of classes scores. So in linear classification, for example, how it works, I just take an input image 2 cross 2, which has the value 56, 231, 24, and 2. I'll just make a matrix linear. For example, this line 56, 231, 24, and 2. This is the simple matrix multiplication. When we multiply these two values and having the Bayes value and addition with the Bayes value, we'll get this value, minus 96.8, 437.9, 61.95. So as you see, this orange color belongs to a cat, this blue color belongs to a dog, and 61.95 share, this green color shows the shape value. So going forward on the convolution neural network, this is just basically we have different layers inside a convolutional neural network, which have a convolution, max pooling, and this type of network, which will be made accordingly and according to the requirement of the image classification. Going further inside, convolution has just, as you know, this is basically an ANN has a different set of mathematical formation, which have weight, which have Bayes values. So basically convolution neural network is basically used to get the features learning from the input image, and then input image, the size of the input image can be varied from, for example, 200 cross 200. So we just minimize their features using the convolution neural network, and then send to the classification model to just find out and classify classify in different classes. So this is basically the formation. I just minimize here and just stop the video here, and you can now easily check it out. For example, this 18 will be multiplied by 1. And you can say the weight values is 101010101. This is the weight value. That means weight is basically the parameter within the neural network that transform input data within the network hidden. So basically the values of the weight is again came from that neural network which is designed to be classified. So the input image is once compared, you can say, or you can just convolve it with having a multiplication. So whenever you just, for example, you just get 18, 1 multiplied by 18, 54 multiplied by 0, 51 multiplied by 1, 55 multiplied by 0, then 121 multiplied by 1, so on. So when you add all these values after the multiplication, When you add all these values, you will get the value 429. Similarly, the upper value is also like this. You can just check it out here. 1 minute. Yeah. For example, this is the same weight which is applied here. So 1 multiply by 1, then 1 multiply by 0, then 1 multiply by 1. After having all these values, these are the 3 cross 3 kernel. So we have different 9 values. So for the first value, when we add multiply it and add it, then the answer will be 4. So now the padding, you can see another component is here, which is a building block for the image classification, which is padding. So padding is normally used to keep the output size similar to the input. For example, if I have the image size of 32 into 32 into 3, and we need to have an output, so we need to add 2 more layers, which can be as an input, which can be used as an output. So we use zero padding. We just add zeros on the left, right, and on all 4 sides of the image. So there is an activation function. Activation function, basically we use normally relo. Relo is generally an activation function, which is basically an input directly. It's positive. Otherwise, it will be a 0 value. So activation function help to produce our network activation performs an embedded non-linearity to the feature space. So this is basically element wise. Each element is you can say you can have the function and apply the output for the convolutional layer. After having an activation function, we have a pooling layer. Pooling layer is basically used to downsample the value. As you see in the figure, in the pink box, we have 1156. So in this case, just the max pool we use and get the maximum. You can see 6 is the maximum value here. So I'll take the 6 on the first pixel value. Similarly, on the next side, you can say 2, 4, 7, 8. Then it will, the next value is, the biggest one is 8. Then on the third one is 3, and the last one is 4. So pooling is basically, this makes the operation for the fully connected layer and computational. As I tell you earlier, that all these operations are performed to just minimize the features to just run inside inside the fully convolutional layers to get the classification result. So fully connected layers are normally used for the classification purpose. We can apply some kind of activation function, some kind of classification method there. Normally we use softmax and some kind of that for the loss function. So fully connected is used again. There can be one fully connected layers and there can be multiple fully connected layers. So loss function is is just to minimize just to minimize the result of the predicted output of the network. That means how many true positive results has been produced, and getting for example, we use softmax function here to find out the multi-class classification. So let's begin with the image classification model. I am just using here a Keras library, which is having a matplotlib and Seaborn to visualize the data here. So this is the basic step is to just import the libraries. I don't know exactly how many people are familiar with Keras and TensorFlow. So just starting with the Keras is the API, high-level API, which is used normally for the image classification. So it has been made above TensorFlow and Theano. So we will have this experimentation here. So just after that, we just import the required libraries. You can see in this slide that you are using Matplotlib. Matplotlib is using for the purpose of plotting images or the results. Then we will have a model which is sequential. Then we are using here a dense layer, conv 2D, max pool 2D, and flattened dropout layers. These are the 5 layers which I'm using in our network. So, flattened layer is normally used here for 1D tensor formation, and the dropout layer is used for some time to just make it out for the overfitting. For example, overfitting means, for example, if you have multiple images and you have a very high training, and sometimes due to noise, there can be some negative results. So that negative results impact out on the main classification results. So we have here the optimizer. There are multiple optimizers, but here in my work, I'm using Adam. So for the scikit-learn, we have another library for the confusion matrix. Scikit-learn basically are used to make a confusion matrix. That means how much accuracy will be performed having true positive, true negative, false positive, and false negative results. Then we have import OpenCV here. And then NumPy mathematical formation. This NumPy library is used for mathematical calculations. So the second step is loading the data. So here we use GAT data, and here we are using rugby and soccer data set. Rugby and data set here. So just use OpenCV IMRead function for the RGB format and resize the images to our desired width and height. In its case, both being means for the images like 224 it cross 224. So this is the code for loading the data. I think I'll just having a practical on this, and you'll easily understand what is this. And then step number 3, we just visualize the data. So I have considered here data for a rugby and a soccer. Both the rugby and soccer have 1200 images in the data set. And we are using these commands here for getting to visualize this data set. So blue color is for rugby and orange color is for soccer. So you can also visualize that image by using a plot imshow command, and any of the random image can be selected here to get visualized on the screen. So step number 4 is data pre-processing and data augmentation. So data augmentation is again very important, because normally we are using data augmentation techniques when the data set is very small. For example, if you have a very less images on a particular class and you need to make the images equal to another class. For example, if one class have 500 images and the other class have 100 images, and you need that 100 images it will equal to 500 of that class, then you will make an augmentation technique where you can just mirror the image, or you can just change the angle of that image. So whenever you do this, the pixel value of that particular image has been changed. So the number of images can be used for the training. So for the pre-processing, we just split the data into three formations. One is train, second one is test, and the third one is validation. So for the training, for example, I have images of maybe I have images of 100. For example, normally we use the ratio of 30-70, means 70% of the data will be gone to the training side, and again the 15% which will be divided into 10% and 20%, 10% for the validation and 20% for the testing. So this is the type of mechanism which we can use in data processing and data augmentation. So in step number 5, we just define the model. Let's define a simple model with 3 convolutional layers, followed with max pooling layers. A dropout layer is added after third max pool operations to avoid overfitting. So it doesn't matter if you will add it overfitting at any time or not, it doesn't matter. But it will be important to have this dropout layer whenever you get a small data set. So you can see this is model.add com2d padding, same. This is just an code here, just adding 3 layers here, 1 dropout layer, and making the dense layer with the activation function relo. As I told you earlier, relo is a linear activation function, rectified linear activation function. So for the classification, we use here softmax. So after having the training done, we need to just evaluate our results. Here we use 500 epochs. Epochs means a number of iterations inside one time. How many times or how many times one training steps can be completed. So here I'm taking 500. This can be changed from depending upon the results. So sometimes when overfitting, for example, if you just test it out from 100, for example, the 100 epochs, then goes to 200, then 300 and 400, just about depending upon which validation accuracy you will get the better on which, how many epochs. So after that, you can see there is validation accuracy, then validation results, validation epochs there. Then after having this, training and validation results. So this is the results after having the training. You can see here the training accuracy and the training and validation accuracy and training and validation loss. So blue color, you can see, you can earlier say that it was blue is blue is for the rugby. So as you see the results of the rugby, I'm just talking about the accuracy first. You can see it's just converging to the 90%. The blue color is converging to the 90%. That means the classification for the rugby images are quite much better as compared to the soccer images. Similarly, the losses are also, you can see, if you see on the loss, the blue color, the training loss is quite much, it's converged to nearby zero. That means the loss is very less on the rugby side. So this is just the precision recall F1 score. We have different results here, 80%, 86%, then having average macro, average accuracy is 83% for different images. So here I'm going to start with some of the practical work. I have using another example to just classify cats and dogs. So I have downloaded our data from Kaggle dataset. You can find easily on the internet, Kaggle dataset. So we have cats and dogs. So I just downloaded the dataset. So there are 3 folders: test, train, and valid. Okay. So we just go inside train first and check out how many images are there. So again, inside train there are 2 folders, cats and dog. So you can see there are 20 files. That means there are inside train there are 20 images of a cat. I'm just taking out, then go inside dog. Now again there are 20 images for a dog. So that means inside a train folder there are 2 subfolders, cat and dog, and each subfolder contains 20 images. Now going towards now again go inside train, then we have test, dir, then we have cat and dog. Okay, inside test there are 5 images. And inside dog Again, it has 5 images of dog. So this is very important to, before having a training on any of the model, we need to first download the data set, proper data set, and split the data set, as I told you earlier, into train, test, and validation. So now what about valid? So again, you have a valid data set, cdcat. Yes, so it has 8 images inside that valid data set. So that means we have 20 images for the training, then we have 5 images for the testing purpose, and then 8 images for the validation. It depends upon you how many said. This is just an example. I'll share the code later on with you people to just play around and just having the results from your side. So now start with the program. You just have an Anaconda installed on your laptop. So just go to the internet and download Anaconda. So Anaconda, I'm using here Jupyter Notebook to run a Keras model here. So I just already made changes and made all the things available for the code here. So as you see in the code, as you saw earlier in the presentation, all the slides, now the code is available here. That all the models are, we first import all the models of the Keras. So this is very important to understand that whenever you install Anaconda, you need to make an environment. So normally you have an environment name with the name base. You can see here base, BASE base here. You can just install different packages here. For example, sklearn, then Keras. So you need a command here to install pip install Keras. So pip install TensorFlow. So these are the installation which I have already done it earlier for having this kind of before the presentation. So first you install the TensorFlow. As I told you that TensorFlow is the base library. Upper on this we install Keras. So after having this installation complete, you have different other different packages to be installed, like OpenCV and other packages, NumPy and other. So whenever, for example, this is the command, you can say pip install TensorFlow. So requirement is already satisfied here. That means I have already installed here. So the installation is, the machine is ready to run. So these are the packages for the installation. Then whenever you install the packages, first you check 1 minute. So inside users, US, you will go Anaconda 3. Then you have lib. So these are the packages which you have installed. Okay. So one more important thing, whenever the environment is set up, you need to store the particular data set on that environment. For example, I have copied all the files of cats and dogs inside that environment where that Anaconda and these libraries are available to install. Okay. Then go on the code side. From the Keras, you must import other models. For example, here I use a sequential model, which where I use dense, dropout, and flatten layers. So for the Keras model, we import a 2D conv model. As there are 2-dimensional, we are talking about the 2-dimensional convolution layers. That's why I'm using here conv 2D. Then we are using max pooling, again 2D. Then we use an optimizer Adam that will finally formalize the best results for the classification. And then we have Keras utilities, where we use categorical cross entropy. So categorical cross entropy is basically we can use for the loss function, where we normally use two types of kind of classification, either one or two, either 1 or 0. So categorical cross entropy we are using here. Then we use NumPy. NumPy is again using the mathematical formation, then using the pandas and having matplotlib, and then these using this. So again, now for the first step we have just imported. Then the next step, we are going to just configure the path where all these folders which you have seen earlier, train, valid, and test, are available. For example, as you see here, cats and dogs. So just cats and dogs, we just define train underscore path cats under. So whenever you just copied the folder on inside that particular environment, that means there is no need to give the particular path C:/ like this. There is no need for that, because it will always take the by default that path. So valid.path has valid folder. Then as you see, that train, valid, and test, all these have different images inside. So after that, having on the next step, we are using image data generator. So image data generator is an Keras object used to generate data into batches. So here I use image data generator from the library, from the path, train path, and the target size of the image is 224 cross 224 cross 224 224 cross 224, and having the class dog and cat. And we split the I split the batch the images of images into two batches. One image of 10 one batch of 10 images, and the other one is of 10 images. So similarly, we have valid batches. So we have valid batches. Then again, image generator, follow up from the directory, the same directory. You just need to change the size of the batch 4, because we just take only 5 images. That's why I took just 4 here. So you can change the size according to the data set which you want to classify. Similarly, the test batches, image generator, then this will again have the batch size of 10, or you can say you can minimize it according to yourself. So after that, this code is just basically for plotting the image. How you plot the image using the basic Python libraries which have been already mentioned earlier. So this is just an IM show and just the plotting the image side. Then the next one is image labels next generation. Whenever you just generate the batches, you will get that batch data into the next labels in the variables images and labels. And after that, you will just plot the images and have the accuracy here. So I can just run step by step here. Is I just run the code here. Is it okay? Then all the packages are okay. Then we run again. Okay, the path is okay. Then we can generate here. Yes. Now there are 40 images belong to 2 classes. That means inside that particular test folder, there are 20 images of dogs and cats. Then run this code. And after having this, okay, now you can find the accuracy here. You can find the result here. 1 is for cat, and 0 you can see here. 0 means that there is no dog, and 1 means there is a cat. Here 1 means a dog and 0 means a cat. So similarly, you can see here the results are quite better. So these are the basic results which we get from the Keras library from just making image classifier. So any question up till now?
It's okay, Mr. Fawad. It seems that we don't have any questions. We may continue the presentation.
Okay. So, Okay, so this is code number 1. Now moving forward. Okay, so now I'm going to start with the same thing with the convolutional neural network. The previous one having just an image classification model without a convolution layer. We are just having our own convolution model here. So we all the previous things are same here as you see in the code, and just having a model with the sequential model with COM2D. We have 32-bit and 3x3 activation function relo here. The input size is 224, and 3. Then we are using to make this in a 1D tensor to make using of the flatten layer, then using a dense layer. So dense layer we are using here to just having an activation function before the classification. Then we compile the model with having with the optimizer Adam. Then we use learning rate. So learning rate is another important component here, just to find out how many steps or how many times the prediction is need to be completed and having a better prediction. So we can change the learning rate according to the accuracy we find. So sometime this is the major important hyperparameter where we can change the learning rate of that. So I'm using here a cross. I'm using here a categorical cross entropy, and the matrix is accuracy. So 1 minute. How can I? Yes. So the image classification, the second code is now here. We have just have the same kind of same type of packages required for this code, and have initial 3 steps which we have already done that before. After having this, we have just made this model here, just added this. Once the system is ready or the model is ready, after having plotting the images, then we use a sequential model for the classification. And after having this, we just run it. Okay, then compile the model. And yes, in the last thing, the model.fit command is used normally for the epochs and the training purposes. So here I'm using steps. There are iterations. How many iterations in each epoch is 4. The validation data for the validation step we are using 4, and there are five epochs. So you can see the results of the accuracy, which is not good, 57%. But we can validation accuracy is 68%. Yes, you can say that validation again it is very less. So we can improve it by using or by changing the optimizers from Adam to some other else. So this can be happen. Yes. So this is all from my side. Any question now? Yes, guys, any questions up till now?
No question.
Okay. So that's it. That is the main thing which I have already clear for the image classification using Keras. So if you want you people to run the code from your side because we have some time here. So you can, if you want to run the code yourself, then it will be great. So normally in workshops, just having a presentation, after the presentation, we need to have some kind of, you can say, hands-on. So I may share the code with Fitri.
Okay, Fawad, this no problem. You may share the coding with me. Later I will email every.
Okay. No, Fitri, I just want, if anybody want to have a practice session right now on his laptop, on his or her laptop. So I can guide, or if somebody have any problem on this thing, to run the code on the Keras side, so I may help you out.
Okay, so is there any participants that are doing this coding inside their laptop or computer right now? Is there anyone or anyone who has troubles running the coding?
Yes.
Yeah, we have from. Please unmute your mic, sir.
Yes, please.
I think Mr. Fawad, you may continue the.
Okay, I have finished my presentation here, because
Yes,
in my plan that I just need to share the code, then the people are going to deploy all these things in their laptops.
Hello.
Yeah. So we have,
Yes, Suleiman.
Yeah.
How are you?
Hello.
Hello. Who's
Yes.
there?
So I think hello. Ndanu Sawabakucha.
Oh, okay.
Yeah. I think my view is it's not possible for one to really combine following what you're presenting with practicing the code. But I think I would have loved a situation where we'll have a feedback situation where maybe after the whole of the day, we could go back, look at these issues, and then maybe on individual platforms, we could get back to you for your problem and then see how best we can improve on the system.
Yes. That can be.
That's my thinking.
Yeah, that's great.
Thank
But
you.
we can have some discussion out of it. If somebody have any questions regarding anything in the presentation or inside the code for the Keras and TensorFlow or the setup, I may help you out, and I'm glad to have.
Yeah, the presentation is well organized, and I think I'm in tune with what is happening. As far as I'm concerned, I think it's well presented.
Yeah.
And we hope to make more collaborations and how best we can improve our in-depth knowledge about this whole issue. Thank you.
Okay, thank you very much.
Mr. Nanjunis. Okay, maybe Fawad, you continue the present. If there are any troubles that they have, they can email us back based on the email we emailed to their email domain, and then I will forward it, especially questions to you.
Okay. So I have finished my presentation here. So over to you, Fitri.
Oh, okay. So you have finished your.
Yeah.
Okay. Thank you, Mr. Fawad. Dear participants, unfortunately, we have reached the end of our workshop for today. For the last session, I'd like to request the participants to switch on their webcams and smile so that we can take pictures together for our own record. For your information, there has been a change for the emailing process. We will email every participant that join us based on the list of participants that we obtained at the end of the workshop. The email will be sent to the registered email domain that you have provided during the registration form. So the email will contain the recording link, also the certificates, and also you may email us your question if there's any troubles that you encountered during running the coding. So may I have everyone to open their webcam?
Assalamualaikum Fitri.
Yes.